In the first section, for line segment properties, we'll review some terminology, explore the cross product, look at what the definition of a turn would mean when encountering two line segments, and what the intersection can help us with, what the intersection of two line segments can help us with. Line segments. Here's some basic terminology. If you let P1 be denoted by x1, y1, and P2 be denoted by x2, y2, then you have defined two distinct points in a plane. The convex combination series, or it's really a scalar representation that can be applied to P1 and P2. So therefore, P3 falls somewhere on this line between P1 and P2. Again, or alpha, represented here as I just referred to as the scalar, must range between 0 and 1. So if alpha was 0 here, it would have no influence from P1 and be 100% from P2, or P3 would equal P2 in this case, or vice versa. If alpha was 1, P3 would equal P1, and it would lie, the second point would lie on P1 and have no influence from P2. If alpha was 0.5, or exactly halfway between 0 and 1, this would be a point, P3 would be a point between P1 and P2. A line segment is a set of convex combinations of P1 and P2, again, are two distinct points. So P3 is some alpha combination. You could have a beta that was a different level between 0 and 1, which would give you a P4 that is somewhere between P1 and P2. But it's also on this line, so it's collinear, the combination creating a line, collinear between points P1 and P2. Something right now to note that we'll get to in the directed segments is P1 and P2, when they are labeled as a line segment, it just indicates a series of connections between P1 and P2. It doesn't indicate in which direction you're actually moving. Important later. The endpoints. Given a segment P1 and P2, which we just learned the definition of, then P1 and P2 are the terminal points for that segment, or they're the absolute boundary points for that segment. Now, as I pointed before, in a convex combination, you could have alpha set to 0, where the point could lie on P3, could lie on P2. But the 2 points that when you actually label these 2 points, P1 to P2, that's what you're accounting for. So even though there could be a point on the endpoints, once you've given this designation, P1 and P2, that could be considered your origin at some point. But that's what's important to note, is that in this notation, P1 and P2 represent the ends of the line. A directed segment. Directed segments are given a specific ordering of two distinct points that form a line segment. So this directed segment is P1 first, endpoint 1, endpoint 2 is P2. If you had P2, P1, the line, this notation would be reversed. It'd have P1, P2, but the line segment would still be going to the right. That is your general notation. So the line segment P1, P2, or the directed line segment P1, P2, also indicates which comes first and which comes second. A vector. If the directed line segment starts at the origin, 0, 0 generally, then the directed segment can be treated as a vector P2. So when you have a starting point for the vector and a direction for it, so if the origin was P1 and P2 was some other distinct point, then moving in that direction from the origin to P2, you would have the directed segment also considered a vector. the cross product. So let P1 and P2 be vectors. So again, to review, origin, then the line segment, the directed segment from origin to P2 and origin to P1 would be a vector. And that fits the definition as described previously. Now, the cross product is defined as this X is really a cross product symbol. It's the determinant x1, x2, y1, y2, or simply put, x1 times x2 minus x2 times x1. So if you take this plane, defined here, your standard xy coordinate system, and you have the directed segment P0 or origin to P1, and you have the directed segment origin to P2, taking the cross product of the two, so some type of influence of P2, some type of influence of P1, and you'll get this point out here. This signed area, or the area covered by both of these vectors and the cross product of the vectors, give you this area below. And this is going to be important later when we talk about the distance between points or the distance between lines and what really, how would you determine which is the direction that you're going. So all of these points will be used later. So right now it's important to note that you can find some type of area between two vectors, and that way you can quantify the difference between two different vectors and their cross products by the signed area of the vectors. Turns. So again, here's our notation for our cross product. If the cross product is greater than 0, then P1 is clockwise. Again, this order is important. In this ordering, P1 is clockwise from P2 with respect to the origin if it's greater than 0. If the cross product is 0, then P1 and P2 are collinear and they lie on the same line. If the cross product is less than 0, then P1 is counterclockwise from P2 with respect to the origin. So you can always, of course, have an angle between them, which is defined with this notation. The angle, what is your starting point? Here's a vector, starting point, and here's your second vector. And this notation is really the difference of P1, cross product, difference of P2. Now, in general, why did you not see that applied before? And that's because we started at 0, 0. If P0 was not the origin, this is the adjustment you would need to make to be able to evaluate the cross product starting from a given point. And this general definition fits the specific case of the origin, but it also allows us the flexibility to evaluate when we have a set of points that are randomly spaced throughout a surface. So taking these three criteria and trying to give them a graphical example. If the cross product, this area, is greater than 0, then we have this clockwise rotation. So P1 to P2, it's going to rotate to the right, or as a clock would also rotate. 0, again, it's collinear, and the two vectors lie in line with each other. Now, if the cross product is less than 0, then P1 would have to rotate the opposite direction of a clock's rotation, or counterclockwise, to get to P2. And these are all important criteria later, especially when we look at a convex hull that relies on this notation to keep a standard of criteria evaluation between points. The intersection. If and only if either or both conditions hold. Each segment straddles the line containing the other, or if and only if an endpoint of one segment lies on the other segment. So here's the endpoint, 0 lies on the other segment. And in all of these examples, clockwise, counterclockwise, collinear, they do intersect because origin, considered the endpoint of each of these vectors, lies on both. So based on this intersection definition, each of these vectors do intersect. So keep in mind this terminology because all of these definitions are used in later sections to better to define and speed up a brute force algorithm to a more elegant algorithm.